Next, we examine the inverse of a function. So this would be the inverse of a function. So if we have a function f, its inverse is usually denoted by f with a superscript -1. So this would be read f inverse, and then f inverse of x is just literally f inverse of x. So what is this inverse function? So the inverse function is basically the function that takes the output and then tells you which input would generate that output. So it does the opposite of the function f. So if y is equal to f of x, that would be true if and only if x is equal to f inverse of y. So we have to say if f is invertible. So it's not always possible to get an inverse function, so let me just write a little caveat on the side. If f is an invertible function, then y equals f of x if and only if x is equal to f inverse of y. So in other words, the function f starts with the input and gives you the output. Now suppose you have an output and you want to know where it came from. Then you say, well, what's f inverse of that output? And it tells me the input. So let's look at an example. Let's look at a table. So let's say we have a table where we have some x values, 0, 1, 2, 3, 4, 5, and some outputs, 6, 3, 12, 5, 14, 7. And we say y is equal to f of x. So for example, f of 3 is equal to 5. Right? So the input was 3, which we pick up right here, and then the output is 5. So f of 3 is equal to 5. Now if you want to say what's f inverse of 5, you would get 3. So f inverse of 5 is equal to 3. Because this is asking, well, what x value gave me that y value? So it's the x value of 3 that gives me the y value of 5. Similarly, we can say f inverse of 3 is equal to, well, let's take a look. So this says f inverse of 3. So that says the output was 3. What was the input? So we look at our outputs. So the output 3, the input was 1. So f inverse of 3 is equal to 1. And notice that f of 1 is equal to 3. So when is a function invertible? So when is a function invertible? So let's just go back and write down what a function is. So a function is a rule that assigns a unique output to every input, basically, every input. So every element of the domain. So for every input, there's a unique output. So for a function to be invertible, it also has to be true that every output has a unique input. So for a function to be invertible, every output must match up with a single input, with a single unique input. So let's think about this example where we have people in your classroom and the function was their age. These are maybe little genies, or maybe they're doing some sort of gymnastics. It's just a quick stick figure. So let's say we have John, Sally, Danish, Joe, and Edgar. And the function returns the age of the student. So John is 22, Sally is 19, Danish is 18, Joe is 19, and Edgar is 21. So this is a function, so f goes from the person to the age. So the question is this function invertible? Notice that every person has a single age assigned to them. John is 22. You wouldn't say John is 22 and 27, right? He has only a single age, so this is a function. So the question is this function invertible? And to figure out the answer to that question, we have to look at the outputs and say, is each age assigned to a unique input? Well, as it turns out, the answer is no, because 19 is assigned to two inputs. So 19 matches up with Sally, and it matches up with Joe. So you would say f inverse of 19, well, it has to have a uniquely specified output. There can only be one person in the classroom whose age is 19. In this case, there are two people, so the inverse, so the function is not invertible. It does not have an inverse, because the inverse would not be a function. So basically, every input has to have a single output, and then each output has to only come from that input. So once the output is used once, you've used it up. You can't use it again. So once you assign age 22 to John, nobody else can have age of 22. Once you assign 19 to Sally, nobody else can be of the age 19, and so forth. So normally, just to require f to be a function, it's okay to use outputs for multiple inputs. It's like it's okay for different people in a classroom to have the same age. But in order for a function to be invertible, it has a higher standard. You can only use each output once, so that each output is uniquely matched with its corresponding input. So you can go from input to output and output to input uniquely. And that has a special name. It's called one-to-one. One-to-one. So a function is one-to-one if every output is matched precisely with single input, and vice versa. So basically, every input has a unique output, every output has a unique input. Let's see what this looks like on a graph. So here we have a graph of an invertible function. Right, because every input, every x value has a single corresponding y value. So this would be x1, y1. And notice that I can only use this y value once. So once I use that y value, I can't use that y value again. So in other words, for a function to be an invertible, in addition to it satisfying the vertical line test, it must also satisfy a horizontal line test. So f must also satisfy a horizontal line test, meaning that any horizontal line can intersect the graph at most one time, just like any vertical line can intersect the graph at most one time. So here we have, a value x2, and it returns a y value, y2, and that's the only time y2 is used. So x2 and y2 correspond to each other. The function is one-to-one. This x2 has a y2, and that y2 has just this x2. You don't have two separate x values leading to the same y value. And so that way you can say that, well, y is a function of x, so you can go from x to the y value, or you can say y or x is a function of y. So you can start with the y and go the opposite way and figure out, backtrack to your original x. So basically it goes both ways. So final thing about invertible functions, so if f inverse is the inverse of f, then the graph of f inverse and f are reflections of each other about the line y is equal to x. So if you, for example, so there's y is equal to x squared, and here's y is equal to the square root of x. And here's the line y is equal to x. So basically, the function and its inverse, are reflections of each other about the line y is equal to x. Another thing to note about inverse functions is that they literally undo each other. So if f of x is equal to x squared, then f inverse of x is the square root of x. So in other words, if you square, so for example, if you say f of 3 is equal to 9, so f inverse of 9 would equal 3. It's pretty clear that if to go from the input to the output you square it, then to go from the output back to the input you have to take the square root. So basically the inverse function is something that undoes the original function. Another way of looking at that is to say that f of f inverse of x is equal to x. Now we've seen this before. We saw some properties with logarithms. We saw that e to the ln of x is equal to x, and ln of e to the x is equal to x. So this basically implies that the two functions e to the x and ln of x are inverses of each other. And this means function inverses of each other. One undoes the other one, right? So for example, so let's work it out in some more detail. Let's say we have f of x is equal to e to the x. I'm claiming that f inverse of x is ln of x. Well, let's try it. Let's do f of 2. F of 2 is equal to e to the 2. So how do we get from this output, so here's my output, back to the input? Well, we have to take the natural log. So let's try f inverse of e squared. So that would be the ln of e squared. So you can remember that ln of e to the x is just x, or you can move that guy out front, and it's 2 ln of e, and ln of e is just 1, so it's equal to 2. So it definitely works. Furthermore, if we think about the graphs, so here's 1, and there's 1. So if I think about the graph of e to the x, that's y is equal to e to the x. I'll say f of x is equal to e to the x. For negative x values, it gets smaller and smaller and smaller, and it basically decays exponentially as x goes to minus infinity. And it hits y is equal to 1 when x is equal to 0, then it goes up to infinity as x goes to infinity, so it grows exponentially. Now, ln of x, on the other hand, starts down here, very close to the y-axis, passes through x is equal to 1 instead of y is equal to 1, and then grows indefinitely, but slower and slower and slower, just like e to the x is growing faster and faster and faster. And if we think about the line y is equal to x, and down here we had f inverse of x, which is equal to ln of x. We see that the graph for e to the x and the graph for ln of x are a perfect reflection of each other about the line y is equal to x.